Okay, wonderful. Just started the recording, and here we are today, July 7th. We have a multitude of announcements here. Let's start with our announcements for today's lecture. Office hours this week. This is a special week, as you know. We were affected by a recent holiday, and let me just adjust the monitor a little bit here. Yep, there we go. Okay, and yeah. And we have an exam Friday. So these are my office hours for this week. You can check with Chris. And I wanted to clarify the grading policy. It's different for different courses. This particular course was not offered last summer, so we don't have a reference point for last summer. We're going to be using the mastery of concepts. And to emphasize, the course will not be graded on a curve. Traditionally, this course has been graded on a curve. That means the top 35% of students get an A. And when we say A, that's the union of A plus, A, and A minus. The next 40% of students would get a B, and that's the union of B pluses, Bs, and B minuses, et cetera. We don't have to give these an Fs. Yeah, so given that we have the COVID pandemic and we're doing remote instruction, there's a problem with academic dishonesty. Therefore, it would be very unfair for a dishonest student to unfairly gain an advantage. And for example, a student who would have gotten an A gets bumped down into the Bs. That's not fair. So it's likely that we'll see more than 35% As. We're looking for mastery of concepts, and the grade will be determined using traditional grading in that regard. Okay, a reminder on the prerequisite. There's been some confusion about prerequisites. So at UC Berkeley, we have the 5 sequence and we have the 7 sequence. Either one that consists of A, B, and C, part A, part B, part C. And in doing this, these invoke other prerequisites. So Math 53 is a prerequisite for 5B and 7B. Physics 89, previously it was Math 54, prereq for 5C and 7C. So in summary, there are prerequisites for this course, Physics 105, that include these 2 math courses. And this is really important here, things like partial differentiation and working with matrices, stuff like that. Okay, another remark here, computers. Later in the course this summer, we'll be using computers more. On the current homework assignment, which is homework number 4, you are asked to plot a function. If this is a hardship for you, then please let us know. We will get you the help that you need. There are various people and agencies at UC Berkeley that will help you with that. So yeah, if this is causing you any sort of grief, just let us know, and we'll help you. Also, there are tutoring services if the course material itself is something that you would like a tutor for. There are a variety of tutors available. Some of them are free tutors and some of them are for hire, like you pay them money. Okay, sample exams. I did post one sample exam a couple days ago. I'm going to post another one this evening. Again, what you will see by looking at the sample exams is that the emphasis is on Chapter 7 material for the main structure, but we'll invoke stuff certainly from Chapter 5, the ability to solve a differential equation. Again, that harkens back to these courses where that's covered. With the notion of the general solution, particular solution, oscillatory solutions, et cetera, exponential growth. Okay, so that's it for the announcements. So now, let us resume. We're in the midst of a fascinating story, and what I'll do, we had some discussion in our last meeting. It's a remarkable achievement. This is one of the great achievements of classical physics, to systematically solve a very difficult problem, a 6 degree of freedom problem, and systematically use a variety of techniques to reduce the level of difficulty from 6 degrees of freedom to 3 degrees of freedom, then to 2 degrees of freedom, and then to 1 degree of freedom. And you know, for 1 degree of freedom problems with constancy, a conserved quantity like the energy, we can write down an integral solution. So that structure is something we talked about last time. So yeah, this is a little bit of a busy diagram, but you see the basic structure here. that we have a 6th degree of freedom problem. It begins life, so to speak, with these 6 natural coordinates, x1, y1, z1. Those are the coordinates of particle number 1. x2, y2, z2, those are the coordinates of particle number 2. So you can write out a Lagrangian. It would be a function of 12 variables, right? You have 6 coordinates and then the q dots, right? So in general, we speak of q's and q dots. Then last time we talked about how you reduce the level of difficulty to 3 degrees of freedom. And this was a wonderful opportunity. Remember, one of our objectives this week, because we have an exam on Friday, one of our objectives this week is to review material from chapter 7 that you need for the exam. And the ability to take a Lagrangian and transform it to different coordinates, this is certainly amongst our foundation skills from chapter 7. Okay, so that's, we'll talk about this more today. There is a transformation that occurs here. Something we talked about last time, we defined, actually I should say, we took some time to recall the definitions of some fundamental terminology that we use in the course. An equation of motion is a differential equation that remains to be solved. You haven't solved the problem yet. A major milestone to get to an equation of motion. And we have a prescription in the Lagrangian formulation of mechanics. We have a prescription how to take a Lagrangian and how to extract an equation of motion. Once you have the equation of motion, then we must invoke our mathematics skills to solve the differential equation to actually get the solution. The position of a particle as a function of time, that would be one example. Later, we'll talk about rigid objects, maybe a spaceship, if you have a rigid spaceship, and maybe it's rotating in a complicated manner. So that would be something more complicated than the motion of a point particle. But the time evolution of the system, no matter how you choose to describe it mathematically, we're going to need some formulas for the time evolution of the system, and that's called the solution to the equation of motion. It's also called the trajectory, and in the language used by theorists, it's called the orbit of the system. That's to invoke a diagram where you have a multidimensional space and you have a certain path through that space. That's the time evolution of your system. Okay, so we're going to go through this again today. Again, we want to seize every opportunity to review material for the exam. So let's talk about these transformations that we did last time. Okay. Okay, so this is the first stage in our journey. We want to really understand all the aspects of this transformation, going from 6 degrees of freedom to 3 degrees of freedom. Let's appreciate some of the things that are going on there. And yep, this is what we did. Again, I will use this sheet of paper, which is from our last meeting. You see the date there. Let's move it so you can see the date on the camera. This was yesterday. This is what we did. This is a wonderful opportunity to recall how you change coordinates. Remember the fundamental structure. The Lagrangian is the kinetic energy minus the potential energy. Okay. Here, in this equation, which I'm pointing to with the pen, we have expressed the Lagrangian using the original 6 coordinates. You see the individual x1 dot, x2 dot, x1 dot, y1 dot, z1 dot, those are here. x2 dot, y2 dot, and z2 dot, those are here. And this r is shorthand for this wonderful square root, the interparticle separation, the distance between the 2 particles. So the important thing to appreciate here is that the Lagrangian is a scalar, right? The kinetic energy is a scalar. It does not have a direction. The potential energy is a scalar, and we're just subtracting kinetic minus potential. And here we have expressed those 2 scalars using the original, the so-called old coordinates, right? When we do a transformation, we can use this terminology, old coordinates, new coordinates, we're transforming the Lagrangian from the old coordinates to the new coordinates. Okay, so the big picture is you transform, right? So in this box here, well, let me rephrase that differently. You take this expression here, kinetic energy minus potential, and you write down the kinetic energy in the new coordinates, and then you subtract from that the potential energy, again, in the new coordinates. So again, with a reference to the big picture, we're transforming the Lagrangian. Remember the terminology that we used. We have this notion of equations of motion. We could have gone a different route, right? We could have taken this Lagrangian in the old coordinates, applied the Euler-Lagrange equations. That's a prescription to produce equations of motion from a Lagrangian. So those are differential equations. And then we could have transformed those differential equations to the new coordinates. All right. So let's remark down here at the bottom of this paper, you have the Lagrangian. Okay. We have the Lagrangian in the old coordinates, and we have a prescription. We know how to get equations of motion in the old coordinates. So this abbreviation EOM, it's extremely popular abbreviation for equation of motion. We know how to get the equations of motion in the old coordinates. Okay. We can certainly do that. Now notice what's very important to us is to be able to transform the Lagrangian. So what we did in our last meeting, we took the Lagrangian in the old coordinates, we transformed it to the new coordinates. The result is up here. See what we did? There's Lagrangian in the old coordinates. We transformed, there's some algebra. We skipped the algebra. It's fairly elementary. You get this wonderful result. With careful bookkeeping, we recognize the so-called reduced mass. This product over the sum is the reduced mass. We'll be calling that lowercase mu. Okay, but the point is we transformed the Lagrangian. So what we did last time is we went from this Lagrangian over to here like this, and then you can get the equation of motion, the equations of motion. Okay, so there's one remaining thing to talk about in this picture. We could also go this route. It's important to appreciate that this path, you see there are two paths. In our last meeting, we went this route. You could also go this route. Of course, you get the same answer. What we did in our last meeting is we went this way to really review and appreciate the Lagrangian formulation of classical mechanics. But notice, you can also go this route. Here we transform. And so for people who have not studied the Lagrangian formulation of classical mechanics, they would start here. They would take Newton's second law. Okay. So for people who have not studied the Lagrangian formulation of mechanics, they can go this route and they can get the right answer. Let's appreciate that does exist as a path to the solution. You can start with Newton's second law, force equals mass times acceleration. You can get the equations of motion. It's just writing this out. And then you can transform to the new coordinates. So certainly that route is possible. But what we wanted to do is emphasize this as an opportunity to understand our, to really exercise and what's it called, cement our understanding of the Lagrangian approach. The reason is later in the course, we'll be using the Lagrangian approach to solve very difficult problems which cannot easily be solved in this manner. They're extraordinarily difficult and non-intuitive. You have to really have some spectacular insights to go this route. So later in the course, we'll see how the Lagrangian formulation really shines by going this right here. Okay, so let's return then to the main plot. we did transform the Lagrangian, and notice, this is at the end of our last meeting, we were looking at this term. This is called the so-called center of mass Lagrangian, and notice the structure is that of a free particle, a particle of mass capital M, and there is no dependence on capital X, capital Y, and capital Z. Of course, we do have capital X dot, capital Y dot, and capital Z dot. Okay, so we know the solution. In particular, we have the constancy of the momentum. Okay. It follows using our skills from chapter 7. We observe that this quantity is conserved. So the value of the constant, of course, depends on the initial conditions. When you prepare the system and then release it and let it go, you have chosen values for the initial conditions, and those initial conditions determine this constant. Once you have that, of course, solving this equation is very easy. You just get that the center of mass, capital R, moves through a three-dimensional space at a constant velocity. And the constant velocity is this constant divided by capital M. So we're well versed in the solution of this equation. All right, this portion we've solved. And so the remaining task is to solve this. And notice the differential equation is decoupled. So our remaining task is to solve for the relative motion. And having said that, we have truly arrived at this point here. We want to appreciate this first step in our journey. Now we have a 3 degree of freedom problem. Okay, and what is that 3 degree of freedom problem? We drew some pictures last time. Let's just remind ourselves. This picture here shows the problem. We have a three-dimensional space. The black, X, Y, and Z, we have three axes mutually perpendicular. That conjures up an image of a three-dimensional space. And we have a single particle. There's only one particle now. The mass is mu, which is the reduced mass, the product over the sum. Okay, and this moves under the influence of a force field. There is now a force center. The origin plays a special role. The potential depends only on the distance from this particle to the origin. Okay, so it's a fundamentally different setup. Notice there's some danger of confusion. In the original picture, we had X, Y, and Z axes. These were, again, to conjure up an image of the Cartesian axes. But the important thing is we had these 6 variables, X1, Y1, Z1, X2, Y2, Z2. Okay, now for the relative motion, again, the lowercase r vector is this vector difference. We have this equivalent problem. So you could call this the equivalent 3 degree of freedom problem. That language is used later in the chapter. There's a so-called equivalent 1 degree of freedom problem. And very much in the same sense, this is the equivalent 3 degree of freedom problem. We now have the problem of a single particle of mass mu moving in a three-dimensional space under the influence of a conservative vector field, right? Now the origin plays a special role. In the original problem, the origin did not play a special role. The potential energy only depended on the interparticle separation, right? Remember when we talked about Noether's theorem? This system possesses a translation symmetry. If you move both particles by the same displacement vector, the energy is unchanged. The potential energy is unchanged. Okay. In this picture here, for the 3 degree of freedom problem, there is no translation symmetry. There is a rotational symmetry. We're going to talk about what that means. If you rotate the system, both the kinetic energy as a certain operator, as an expression, is invariant under rotations, and the potential energy as a standard function is invariant under rotations. Okay, so what we're going to do is investigate this further, and we'll take a special, we'll make some effort. We'll take an opportunity to point out there is a pitfall here, a standard pitfall in using Lagrangian mechanics. So we'll go through that very much in detail to emphasize that pitfall that can possibly occur. Okay. So the thing to note here, when we reach this 3 degree of freedom problem, Okay, let's again, we're looking at, these are our notes from our last meeting, okay? This is the relative Lagrangian. What I'll do is I'll copy it over. This is now the starting point for our 3 degree of freedom discussion. I'll copy it over, just a slight change in notation. This product over the sum of the masses, that's what we call lowercase mu. Okay, so I copied over the Lagrangian. In our last meeting, we called this the relative Lagrangian. But since we have completely solved the motion for the center of mass, and since this is the remaining problem to be solved, we'll simply call this Lagrangian now. Okay. Now, the term that is used here is it's rotationally invariant. And let's appreciate what that means. We're going to begin with the remark, we could do the following. We're actually not going to do this, but we could do it. We could transform to spherical coordinates, right? Notice in this problem, we have our notation. This is the standard notation that we like to use. The lowercase r vector denotes x, y, z. We could transform to spherical coordinates. Okay, it's very important to understand. We could do this. As you know, one thing we studied intensively was basically the same transformation, but in a 2-dimensional space. We looked at the following calculation very closely. We talked about a particle moving in a 2-dimensional space, and we had a kinetic energy that looked like this, right? You had an x dot squared plus a y dot squared. That was your squared velocity. And then we transformed it to plane polar coordinates. And in our book, plane polar coordinates, we use r and phi as the plane polar coordinates. So that's very important for the midterm exam, is to understand how to transform it. Very similar story for 3 degrees of freedom. You have these 3 variables, x, y, z, and here's the Lagrangian written in terms of x, y, z. Now it's understood that r is the square root right? That r is just shorthand. It's a little bit of a time saver, but we must be clear that this Lagrangian is a function of x, y, z, and x dot, y dot, z dot, a function of those 6 variables. There's no explicit time dependence here. So this Lagrangian should be thought of as a function of those 6 variables. And you could transform it to be a function of r theta phi, r dot theta dot phi dot. Okay, that's doable. If you did that, what you would see is that since the potential depends only on r, ultimately there would be, you would see this conservation of angular momentum, and there would be no phi dependence, okay? Okay. It turns out this is an interesting statement, and then we'll see how this relates to Lz, the z component of momentum. Angular momentum is a constant. All right. So let's say a few more words about this before we move on. Again, we're not going to go into this calculation, but let's appreciate that when you define spherical coordinates, in some sense you spoil the symmetry, because for spherical coordinates, you choose a reference direction. We typically use the z-axis as our reference direction. And the very definitions of these angles, theta and phi, then will depend on your choice of, first of all, the z-axis, and then phi. That depends on your choice of an x-axis in the plane perpendicular to the z-axis. Okay, so there's some arbitrariness there. When you do the transformation, you get a Lagrangian that has no explicit phi dependence. There is a theta dependence. Okay, so for this transformation, you immediately get that the z component of angular momentum is conserved. But in fact, a stronger statement is true. Every component of the angular momentum is conserved for this problem. Okay, so you could then define a different spherical coordinate system, having chosen a different reference axis for theta, the co-latitude. Again, our purpose right now is to appreciate the fact that you could transform the Lagrangian to different coordinates. There would be a so-called ignorable coordinate. So for example, in this case, there'd be no phi dependence. From that, you get immediately, right, if a coordinate is absent, then the Euler-Lagrange equations tell you that partial L, partial phi dot is a constant. Okay, so we're going to proceed in a different manner, right? And again, we want to highlight the two schools of thought. You can do calculations with the Lagrangian formulation, or you can look at the equations of motion. So what we're going to actually do now is look at the equations of motion, right? We're going to look at the equations of motion and show that, let's indicate the flow of logic like this. This is an arrow indicating the flow of logic. We're going to show that all three components of the angular momentum are conserved. Okay. So it's important to appreciate these two schools of thought. This first calculation is very much in the spirit of Lagrangian mechanics. The second calculation, again, it's available to those people who have not yet studied Lagrangian mechanics. And let's appreciate how that calculation works. Okay, so what we do, we define the angular momentum, okay? So let's be very clear, because there is often confusion about the angular momentum. Let's define the angular momentum for the 3 degree of freedom problem. Okay. Angular momentum for 3 degree of freedom problem. There is a wonderful calculation which we will talk about momentarily. We're going to show that this angular momentum for the 3 degree of freedom problem, and remember what that is. You have a particle of mass mu moving around in a 3-dimensional space. There's only one particle, and you know the definition. You have an r cross p. As always, for angular momentum, you must be clear on the choice of origin. And for this 3 degree of freedom problem, remember we said there is a preferred point. The origin plays a special role, right? Here's the picture. Yes, indeed, here's the picture. And for this 3 degree of freedom problem, the origin plays a special role. There's a force center, okay? And we're going to compute the angular momentum about that origin. The remarkable result, which we'll talk about in a moment, is for the 6 degree of freedom problem, you can define the angular momentum of the 2 particles. We're talking about a sum of 2 contributions, okay? Total. Remember, it's a 2-particle system. For the 6 degree of freedom problem, it's a 2-particle system. The total angular momentum is a sum of 2 contributions, one from particle 1 and another from particle 2. The total angular momentum about the center of mass. Okay. This is crucial that we appreciate what's going on with this statement. Anytime you talk about angular momentum, you must specify an origin. Okay, and what we're saying here, at any instant in the motion of the system, okay, at any instant you can compute the center of mass, right? Obviously it's on the straight line segment between the 2 particles. You can compute the center of mass, you can compute the angular momentum of particle number 1 about that location, and you can compute the angular momentum of particle 2 about that location, and then you do the vector sum of those contributions to get the total angular momentum about the center of mass. It turns out it's equal to this. Remember, the 3 degree of freedom problem has 1 particle with mass mu. Okay, So that's a remarkable calculation that these two are equal. And again, as I emphasize, we must be cognizant of the mathematical framework. When we say 6 degrees of freedom, there are two particles present. Okay, we're talking about the total angular momentum of those two particles about, and you must specify the point, it's about the center of mass, which of course is moving through space. Turns out that this capital L is equal to this capital L. So we'll prove that later today. But for the moment, let's return to our analysis of the 3 degree of freedom problem. Once we're here in this world of the 3 degree of freedom problem, there's no longer any direct reference to the original two particles, right? We have a single particle of mass mu, all right? That's why you could call this the equivalent 3 degree of freedom problem. There is a single particle of mass mu. Mu, in general, does not equal m1 or m2. This is a different particle, it has a different mass. Okay, so here's what we're going to do. This angular momentum, R cross P. This is one of the most fundamental things in physics. For a point particle, the angular momentum, right? We love cross products, no doubt about it. R cross P, what's the momentum? The momentum is mu times r dot. So this is the angular momentum. Let's compute the time derivative. This is the definition of the angular momentum. Let's compute the time derivative. Okay, so there are two terms. You see the first term, because the cross product just consists of some bookkeeping, it's a glorified collection of a bunch of individual products of functions, okay? And therefore, when you compute the time derivative of a cross product of two vectors, you get two terms, just like for the standard product rule. We're getting this r dot crossed into this mu r dot. Of course, that's going to be 0 because the two vectors are parallel. There's another term. We copy over the first factor, and now we must write the time derivative of the second factor. Okay, so notice this one is 0 because you have two vectors that are parallel. So we got a 0 there. This one is 0 because we are dealing with a central force. The force is either pointing in the same direction as r or in the opposite. So a positive or a negative constant times r. The two vectors are parallel, so we get a 0. Okay, but let's again talk about the high level structure. What we have done here is use the equation of motion. For this, notice I drew an arrow down here. We define the angular momentum, we compute the time derivative, and we see that it's 0 using the equation of motion, right? Here we have the equation of motion. There's a force acting on the particle. Okay, and that equation of motion came from our Lagrangian. Okay, so now we can proceed using this knowledge. We have shown that the angular momentum is conserved. Notice that the angular momentum points in a direction that is perpendicular to the plane defined by the r vector and the velocity vector. And both of those factors are perpendicular. So one of two statements that we can make is that r, this is the notation we like to use. Okay, so that's compact notation. When you read this verbally, you say that the r vector is perpendicular to the L vector. We just observed that the L vector is a constant. Therefore, the r vector is confined to a plane, okay? So the conclusion is the motion is in a two-dimensional plane. The plane perpendicular to L. Okay. So with that observation, now notice that the actual orientation of the plane in space depends on the initial conditions. If you prepare the original two particles with different initial conditions, you're going to get a different L vector. Okay, that's okay. Having established, though, that there's a constant vector L, and the motion must be in the plane perpendicular to that vector, we can now introduce two axes. So you arbitrarily introduce two axes in that two-dimensional plane that's perpendicular to L. Okay. So this is something we studied in chapter 7. Wonderful opportunity to recall. What did we do? Well, here we do the transformation. Remember earlier today we talked about hypothetically going to spherical coordinates. Some effort is required to do that. Now we're in a two-dimensional plane. We're going to do essentially the same thing in a two-dimensional space. That means we're going to transform the Lagrangian to plane polar coordinates. Okay, so we have reached a major milestone in the calculation. We have reached the 2-degree of freedom problem, right? We established that the motion is in a two-dimensional space, a flat Euclidean plane in a three-dimensional space. We arbitrarily introduced two axes. We're going to call them X and Y for simplicity. They should not be confused with the original X and Y axes. Okay, so here we are. Okay, this is our new world. Again, for emphasis, I'll put in parentheses, this is new. This is a new x-axis, new y-axis. We'll avoid a lot of cumbersome notation and just simply call them X and Y. Okay, and here we do transform the Lagrangian to the new coordinates. This is something that we are very well versed in. We know that the Lagrangian, we're going to, oops, there's a phi, there's an r. Here's our particle, mass is still mu, the reduced mass. Okay, we transform. Okay, as you know, this object here, the kinetic energy in a two-dimensional, of a point particle in a two-dimensional space, this is something that we're very familiar with. But let's go through this again because there's an important lesson to be learned, a common pitfall. If you have, we're going to identify a conserved quantity, and if you incorrectly implement the constancy of this quantity, you get the wrong answer. So there's a very important message here that we must learn, and let's really root out all the problems here with this potential pitfall. Okay, so the crucial thing here is to observe the Lagrangian, right? Let's write this out in detail. In principle, having transformed it, in principle, the Lagrangian could have this signature. It turns out there's no dependence on t and there's no dependence on phi. Okay, so let's now investigate the implications of this, right? There's no explicit time dependence. That's the word, those are the words that are used. There is implicit time dependence if you plug in r and theta as function of time. There's no explicit dependence on t. That is to say, we're assuming that this central force has no time dependence. It's a static vector field. As a vector field, it's static. Along the orbit, right? If you evaluate u composed with r of t, then you get a time-dependent object. But this scalar field u is time independent, and the force field that goes with it, as a vector field, it's time independent. Okay, the crucial thing now, there's no dependence on phi. So you know what that means. Since the partial of L with respect to phi is 0, we have a logical implication here. It tells us partial L, partial phi dot is a constant. It's a constant of the motion. It's a different constant for different orbits. Okay, it's not one global constant. Different constant for different orbits. Okay, now let's talk about the correct way to use this important statement and the incorrect way. We don't want anyone to fall. There's a pitfall here. We don't want anyone to go that route and get the wrong answer. Okay, so the correct way to go is first, let's do a side-by-side comparison. This really serves to underscore what's going on here. Correct and incorrect. What's the right way to use this wonderful statement? Okay, what you do is first, let's emphasize this, first, you write out the Euler-Lagrange equations for both r and phi. Okay, the incorrect method, we'll describe it over here. Basically, in a nutshell, what the incorrect method is, you first write out one of the Euler-Lagrange equations, you observe there's a constant of the motion, and then you plug it back into the Lagrangian, hoping to save some time, but in fact, it's a disaster. You do some irreparable damage. So incorrect is first, you write out the Euler-Lagrange, I'll abbreviate like so, Euler-Lagrange equation for phi, right? That's correct. You conclude that this partial L partial phi dot, okay? Let's take a second to talk about partial L partial phi dot. Here's the Lagrangian. We must compute the derivative, the partial derivative with respect to phi dot. There's one occurrence of phi dot and it's phi dot squared. So this is equal to, right? The 2 cancels like so very nicely. We got a mu. We got an r squared. We got phi dot, okay? So you see the structure, mu r squared, that's the moment of inertia about the origin. Phi dot, that's angular velocity. Certainly this thing is the z component, right? There's a z component perpendicular, well, I was gonna hold the pen perpendicular to the paper. There's a z direction, right? So even though we're in a 2-dimensional space, one speaks of the z component of the angular momentum, right? So this is Lz, and I'll put that right about here. Yeah, Lz like so. And we also like to call this cursive lowercase l. So be on the lookout. Both of those notations are used. Okay, so the incorrect way to go is that you have this conserved quantity. Right, this is a true statement that we have a constant of the motion. Okay, this is constant. And now here's the travesty. Next, you plug this into the Lagrangian. I want to really emphasize this is wrong. Yeah, this is wrong. You can tell I'm mad because that's all caps. And I'm going to get madder. Putting some red color here. This is wrong. Yeah, I will flunk you immediately if you do this on the exam. I'm kidding. That's a really mean thing to say. I just wanted to liven it up here. Okay, suppose you do this. Then you have the Lagrangian. There's the Lagrangian. Okay. Well, you see what's going on here. Phi dot is the lowercase l over mu r squared. So what you would do is say the Lagrangian is 1/2 mu r dot squared. I simply copied that over. Okay, but now there's an r squared, And we want to understand why this is wrong. And there's a phi dot squared. So what is phi dot squared? Well, you would say phi dot is this quotient. There's a script lowercase l. There's a mu r squared. That thing squared. Okay. And minus u of r. Minus u of r. Okay. So this is wrong. But notice this looks nice. It sure looks nice. It looks like you have a Lagrangian that's a function of r and r dot. It sure looks like you achieved the goal of getting to a 1 degree of freedom problem. Okay. Now you would say, I got a Lagrangian, partial L, partial R, minus the total time derivative of partial L, partial R dot equals 0. Okay, so we want to talk about why this is wrong, and we'll say a few more words about that. Before we do that, basically the short answer is, now when you compute these partial derivatives, there's an incorrect dependence on lowercase r, right? The prescription is to compute a partial derivative with respect to r, and now we have this r. Notice it's r squared over r to the fourth. Obviously that cleans up to be r to the minus second power. But this is now an incorrect partial derivative. Okay, so this is wrong. Let's just really emphasize this again, wrong. Why is it wrong? Well, we never proved it would work. What we proved would work is what we're going to write here on the left. The correct way to go, and let's go through this. You must do this for both. All we're asking you to do is follow the prescription, the Euler-Lagrange prescription for both r and phi. Okay, so this first portion is okay, right? Item number 1, no problem there. L equals mu r squared phi dot. And now the second step, we're doing this for both, right? So there's 1 and there's 2. Let's correctly do this for r. And what does that mean? It means we take this Lagrangian and we must compute a partial derivative with respect to r and a partial derivative with respect to r dot. And now we will meet with success, because when we compute this partial derivative with respect to r, again, we're following the prescription. This is what we proved would work, right? This is looking at chapter 6 and chapter 7. This is the right way to go. You write out the equation of motion for both of your, in this case, there are 2 generalized coordinates. And now we're looking at the r coordinate. So let's talk about the derivative with respect to r. Notice it's r to the plus second power, r squared. When we compute this partial derivative, we must hold, here's the crucial thing. This partial derivative is computed holding all the other variables constant. That's phi dot, and r dot, okay? And so you see, it's r to the plus second power, all right? Without further ado, let's write that one down. Okay, so the 2 cancels like so. We got a mu. We got an r. We got phi dot squared. Okay, so far so good. Here's this thing, minus u prime. U is a function of r, the derivative. That's what we call it. It's a function of a single variable, and the derivative is u prime. It's a very nice compact notation. Okay, so that's the partial, and notice the very important plus sign. All right. The partial derivative with respect to r dot, that's our next objective here. So we look around for r dots. There's only one occurrence of r dot. Looks pretty good. The 2's cancel. U r dot. Okay. And now the prescription, again, the Euler-Lagrange prescription is that the total time derivative of this, that was easy, it's mu times r double dot, is equal to this. Okay. So again, this is correct here. Okay, so what we have here is the correct equation of motion. And there are different ways to organize this. We'll talk about this more later. This thing here, and perhaps I'll use pencil to indicate that I'm making a remark here on top of a calculation we already did. This thing is called the centrifugal force, right? And you know we had a discussion recently. And when we go into chapter 9, we will become experts on this. The centrifugal force, a so-called fictitious force. Okay, that's a little bit, some people don't like that word. It implies we're doing something wrong. Therefore, some people call it an inertial force. It's a force that appears if you are in a non-inertial frame. So in chapter 9, we will become experts on the centrifugal force. But for what we're doing right now, observe that this thing is positive, right? Points away from the origin. That's what we know about centrifugal forces. If you're in a rotating frame, this force is going to point away, right? We had a discussion recently, center fleeing. The centrifugal force is center fleeing. And again, I'll bring in the red color here. Centrifugal force, center fleeing, that's in terms of standard English, not the greatest standard English, but it means it points away from the center. In contrast to centripetal force, the centripetal force is a real force. If you are forcing a particle to go around a circle, good old uniform circular motion, then you must apply a real force. And that force points towards the center pointing. Okay, so that's important to make this distinction here. So now we have our equation of motion. We can define an effective potential. And now we have achieved a major milestone because the structure of this equation, notice this equation, now you can plug in the constant. Maybe we'll put that here as another remark. Now plug in constant. Now it is safe to do so. And again, why is that true? Because we proved that this would work. Why is this incorrect? Well, we never proved it would work. That means a single counterexample will disprove it. And we can easily find a counterexample by just looking at this motion of the particle, and you see that basically this gives you the wrong sign. That sounds a little boring and not so dramatic. It gives you the wrong sign for the centrifugal potential. But in other problems, it'll do much more devastating damage. But nevertheless, even a single sign error, if you put this thing on a computer and integrate, the particle is going to go in the wrong direction. I mean, it's wrong. Okay, so this is wrong in here. This is correct. Now plug in the constant. And so I think I can squeeze it in here. Okay, what happens if you plug in the constant? You get mu r double dot. Okay, and this is now equal to minus U effective prime. Okay, yeah, I'm kind of squeezing it in here a little. Sorry about that. The typesetting is a little cramped, but it's certainly legible. U plus L squared over 2 mu r squared. A little cramped, but definitely legible. So here we are. This is the celebrated milestone. Remember, we talked about the hierarchy starting with 6 degrees of freedom, going to 3 degrees of freedom, then 2 degrees of freedom, then 1 degree of freedom. At this point, once you eliminate that, find out, which you can now do. I think a little red color would help here. Now plug in. Okay, that's a crucial thing. After you follow the prescription, after you utilize the Euler-Lagrange equation, then you're welcome to plug in this constancy of the motion. And this is wonderful, right? We're plugging in this constant here. And there was a phi dot. We didn't know what to do about that phi dot. But once you plug in the constant, you see that phi dot is just lowercase cursive L over mu r squared. Okay, that goes here. And then it's possible to reorganize here. Careful attention to detail gives us this term. And so you see there's an effective potential. Now let's emphasize here for this 1 degree of freedom problem. Okay, this is the milestone we wanted to achieve to get to this 1 degree of freedom problem. And what is that 1 degree of freedom problem? It is a particle of mass mu moving in a one-dimensional space. Now, here's where sometimes people get confused. The confusing point is, should we say that in fact this r-axis is moving through space and rotating? No, we should not say that, because this is the equivalent 1 degree of freedom problem. Okay, oops, I went off the screen there. So this is the equivalent 1 degree of freedom problem. Again, it's logically separate. It's not directly embedded into the original problem. This is a completely separate problem. It is the problem of a particle of mass mu. Okay, so we have an origin here. We have a particle of mass mu. It is the problem of a particle of mass mu moving in a one-dimensional space under the influence of this effective potential. So there's an effective potential here, U sub F, EFF for effective, that is present here. And of course, the force acting on the particle is minus the gradient. So the one-dimensional gradient is just the derivative. That's what we have here. So yeah, the important thing here for the equivalent problem, it is logically distinct from the original problem. And so it's really not correct to say that this R is a moving axis, moving through space. Not really correct. The right way to think of this is that we have a fixed one-dimensional axis. We have a particle moving along that one-dimensional axis. And the motion is governed by this force field that's minus the gradient of that potential. Okay. So of course, for the Kepler problem, right, this is called the Kepler problem. When you have Newtonian gravity, that's called the Kepler problem. We can draw a picture, and it's a wonderful picture. So again, that's the physical space. That picture shows you the space. It's useful, and people often draw this diagram. This is now a separate diagram. And I'm going to indicate that this is a separate diagram. So there's one diagram showing you the physical space, and there's our particle, and the particle is moving left and right on that axis. Turns out it never crosses the origin. We'll talk about that. Here we go with the diagram. This diagram is useful to, first of all, visualize the effective potential. Right? And also we can understand the behavior of the system. Different regimes. There are different regimes. There's bounded motion, right? Little r, as a function of time, it can be periodic and go back and forth between the so-called classical turning points. There are classical turning points. So all of that becomes clear when you look at the picture. So again, this is the r-axis. We're going to plot the effective potential. Okay, let's use a different color, or perhaps should we use pencil? Yep, pencil. So the effective potential looks like this. Okay, and this is for the Kepler problem, right? What's happening for the Kepler problem, the original U, and let me emphasize that here, the Kepler problem, this is the term that is used by theorists. The Kepler problem, the original U is minus lowercase gamma over r, right? We know for Newtonian gravity, it's an inverse square force, right? It's a central force, inverse square force. It's attractive. And we know that the potential looks like this. The gamma, there's a wonderful little identity here. This is a cool one that this will serve you well. Gamma is capital G, right? The universal gravitational constant times little m little m1, little m2. And that's also equal to capital G times capital M mu, right? Remember, the reduced mass mu was a product over the sum. So if you take the reduced mass and multiply by the sum, that capital M is the sum, it gives you the product. So sometimes this is very useful when you're solving problems, doing homework, etc., to have these two forms available. One or the other may help you to simplify. Okay, so this is the Kepler problem, this particular choice. However, everything we have done, think of this page above this statement, everything we have done is true quite generally. Okay. For example, you could have a simple harmonic oscillator. Right? That is to say, you could have this potential U be proportional to the square of the distance from the origin. It turns out that's another very interesting problem. It has a high degree of symmetry. In the language of quantum mechanics, you have operators, a whole bunch of operators that commute. It's integrable. You have a large kind of maximal number of operators that commute with each other. And we'll talk about this more. For the Kepler problem, there's a high degree of symmetry, and the result is in quantum mechanics for hydrogen, you have this degeneracy, right? The principal quantum number determines the energy. The energy for this problem, for the Schrodinger equation, you have this great degeneracy for the principal quantum number equal to some value. You know, there are different values available for the angular momentum quantum number and the magnetic quantum number, but the energy of the orbital depends only on this. And we're going to make some remarks on the classical problem. There are similar things going on in the classical world. Later in the course, towards the end, when we get to the Hamiltonian formulation. Okay, so let's just observe for the Kepler problem, you should have this picture in mind. And the important thing is that this centrifugal term, okay, notice it's proportional. It's a positive constant times r to the minus second power. This is the so-called centrifugal barrier. The particle cannot get to the origin. It's energetically forbidden because we have this thing that asymptotically goes to plus infinity. Okay, that's for the Kepler problem. As r becomes large, if you go to the right in this picture and r becomes large, then you have this negative constant with a 1 over r. And the centrifugal term is going as 1 over r squared. So eventually it becomes extraordinarily small. If you go to large positive r values, then this centrifugal term, because it's a 1 over r squared term, it becomes negligible. This term here, the minus gamma over r, this is the dominant term. And that's why you see the curve is negative here. So those observations, you have a positive constant times 1 over r squared, tells us it's energetically forbidden for the particle to go to the origin, right? And you can see that based on angular momentum. The only way that could happen is if this little l were 0, if you have the case of 0 angular momentum. Otherwise, the fact that you have a non-zero angular momentum makes it impossible for the particle to reach the origin, because then it would have 0 angular momentum. Okay, so we see this nice term here, the centrifugal term in the potential, providing this barrier. Okay, so you can see there are two basic classes, right? If the total energy, right, we know that for this problem, it's a case of motion in a potential, right? When you look at this differential equation, you see that we have mass times acceleration equaling minus the gradient of potential. There's a conserved quantity. There's yet another conserved quantity, and the constancy of the energy, right, is related to the fact that the Lagrangian has no explicit time dependence. So let's put that here as a remark. Total energy okay. I'm going to actually get a whole nother piece of paper. We need to really talk about this. The fact that this Lagrangian is time independent means that the total energy is conserved. Okay, that's a result that was explained in chapter 7. Let's take some time to talk about it. But before we do that, let's observe that there are basically two regions, right? We've talked about the fact that there are, when you solve differential equations, there are different regions that exhibit different behavior. That'll be true later in the course when we talk about, you know, suppose you have a space station tumbling through space. Right? We'll talk about the angular momentum, the angular velocity vector, and there are different regions that exhibit different behavior. So for now, let's observe that if the total energy is negative, it's useful to draw a reference line in this picture. And remember, this picture was a plot of U effective as a function of R. And here we've drawn a horizontal reference line at a negative value. So let's remark here, negative. This is useful if the total mechanical energy is negative. And again, with this convention, this is a very popular convention that the potential for the gravitational force, that go to 0 and infinity. Very common practice. It leads us to the following kind of statements. If the total mechanical energy is negative, then again, here are the classical turning points. And we have oscillatory motion. The particle is going to move back and forth between these classical turning points. Of course, they exist here on the axis, right? That's our physical space. On the other hand, suppose the total energy is positive. Then we're going to see that and it's useful to draw this reference line. So here's a positive value. Okay. And in this case, we're going to see there's hyperbolic motion. When you take the solution and you reconstruct the motion, right? That's a general feature of the theory of reduction. Once you solve the reduced problem, there's some effort required in general to reconstruct the motion in the original problem. But there's a systematic hierarchy. You can go back up the ladder. So we'll talk about how to reconstruct the motion. And here we're going to see the so-called hyperbolic motion. This will be important when we study, for example, the spacecraft Cassini. The Cassini spacecraft passed by Venus 2 times. It was a very profitable thing to do. It robbed the planet of some energy, right? I don't think they filed an environmental impact report because it's a tiny amount of energy that was taken away from the planet Venus and given to the spacecraft. And that spacecraft was propelled towards the outer parts of the solar system, eventually landing a probe on one of the moons out there, Titan. Okay, so now let's talk about a very general truth here. And this will be very interesting to see how this calculation works. Okay, we're going to prove an amazing statement here. This statement is of interest for its shock value. This is a shocking statement. And perhaps this statement captures some of the amazing things we've been doing. But have a look at this statement. Yeah, like I said, this statement is of interest for its shock value. We've got the total time derivative of the Hamiltonian is minus the partial time derivative of the Lagrangian. Now, is that cool or what? That's a pretty cool statement. We're going to understand this. Again, it's remarkable how compact this formula is. It's a very simple, small formula. Most people are unaware of this result. Again, it's another opportunity for you to amaze your friends and relatives with this cool stuff you're learning in Physics 105. But this is the total time derivative of the Hamiltonian, and it's equal to minus the partial derivative of the Lagrangian, right? Notice the notation, that's a partial derivative. Okay, let's prove this. And notice that there's a special case. We'll put that here, special case. We've talked about this before. If, and we phrase it like this, if the partial derivative of the Lagrangian with respect to time equals 0, then the Hamiltonian is a constant of the motion. Okay, again, let's appreciate, and that follows immediately. So if this partial derivative is 0, then the total time derivative of the Hamiltonian is 0. So the Hamiltonian is constant. And again, the phrase that you hear, the theorists, they say this over and over again, H is constant along an orbit. So that's the phrase you'll hear over and over again. The Hamiltonian is constant along an orbit. It's a different constant for different orbits, right? So that's a clarification. If you just write h equals constant, that's not very clear. Later, we'll talk about functions on phase space. This is not, the Hamiltonian is not a constant across all of phase space, but it is constant along any orbit. It's a different constant for different orbits. Okay. So for example, for the simple harmonic oscillator, here's the Hamiltonian. Later in the course, we'll talk about phase space. You have x and p, and the Hamiltonian is equal to one constant, right? It's a p squared over 2m. There's your kinetic energy. And then we got the k over 2 x squared. So you see the structure. It's a different constant for different, it's not globally a constant, but along an orbit, right? Remember, x and p have different units. So here I've drawn it like this. All right. So h is constant along an orbit. Again, it's not globally constant. This is a little bit too vague. There's an understanding when you utter these words, the Hamiltonian is constant. It's a constant of the motion. It's a different constant for different orbits. So it's 0 if you put it at the center. No problem there. The particle is motionless. Again, this is the simple harmonic oscillator. Particle is motion. All of this is a remark about the simple harmonic oscillator. Constant is 0 there, positive constant again. So we'll talk about this more when we talk about the Hamiltonian formulation. But for what we're doing right now, remember we did define the Hamiltonian in chapter 7. Okay. Remember the Hamiltonian, this is supposed to be a cursive H. What is the definition of the Hamiltonian? For 1 degree of freedom, it's q dot partial L partial q dot minus the Lagrangian. Okay, this is a general discussion now for 1 degree of freedom. The statement is true for higher numbers of degrees of freedom. But let's appreciate what's going on here. 1 degree of freedom, we will use Q, right? We like to use Q for generalized coordinates. For the business at hand, we're talking about the radial motion. So little r is what we're really thinking of for the current problem. But this is true quite generally. And let's take a moment to appreciate this result. Again, what a cool statement. Very characteristic of the remarkable statements that we have in classical mechanics. And it's clear from this, you must have a detailed understanding of the framework, the mathematical framework for this problem. Why would it be true that the partial derivative of the Lagrangian is -1 times the total time derivative? Obviously, we have to understand what the total time derivative is. Okay, so great opportunity to remind ourselves, what is the total time derivative? What does that mean? It means you do functional composition. You have the Hamiltonian. Here's the Hamiltonian. This is the definition of the Hamiltonian. And in this construction, oh, wait a minute. It turns out, yeah, I like to put this guy put him on the document camera. He doesn't like Hamilton, but here's his paw. Yep, there he is. So this was so exciting, enough to wake up. That guy will sleep through anything. Okay, so the important thing is this is a function, right? The Lagrangian, for this discussion, 1 degree of freedom, is a function of q dot, and t, right? And the Hamiltonian, if you follow this prescription, the Hamiltonian is a function of q dot, and t at this point. Later in the course, we'll make a transition to where the Hamiltonian is a function of q, the momentum, and t. So we'll get to that later. Later this summer, we'll be doing that. But for the moment, we have a very clear prescription. The Hamiltonian is simply computed as per this prescription. It's clear. Let's look at the units, right? Joules. Lagrangian is in joules. Here's the Lagrangian differentiated like so. So the dimensions of q dot downstairs, well, whatever generalized coordinate you have, right? It could be an angle or a distance parameter, et cetera, and so forth. The units are going to cancel out perfectly. So it's always good to do a sanity check and check the dimensions. Okay, So now let's prove this. We must compute the total time derivative, okay? So what does that mean here? What does it mean to compute a total time derivative? We take our Hamiltonian and we insert, here's the Hamiltonian, it's a function of q dot and t, and now we insert. This is the crucial thing, and again, we're reviewing important stuff from chapter 7. When you have a total time derivative, you insert q of t. And for q dot, you insert q dot of t. And of course, here's t. So now we're going to compute this time derivative, right? And we have these occurrences of t. Okay, so that's the structure. Okay, we got a problem over here. Let me just get this cat out of here. Okay, you're out of here. So first of all, these remarks are to appreciate the framework of this calculation. What does it mean to compute a total time derivative? That's been a central concept in chapter 6 and chapter 7 to really appreciate what this means, right? To understand the Euler-Lagrange equation, we have to appreciate what's going on here. Okay, so let's get right to work. We're going to compute the total time derivative, okay? Total time derivative of this object. And here we go. We got a q dot. We got partial L, partial q dot, and minus the Lagrangian. Okay, so we must compute the total time derivative. The first thing we look at here, here's a product. So we know what to do. This is equal to q double dot. It's a product, we're going to differentiate that one. And then we copy over the second factor, so that's a partial L, partial q dot. Okay, but it's a product. There's another term where we copy over the first factor, so that's q dot. And we, right, I'm going to write it like this. The total time derivative of the second factor, partial L, partial q dot. Okay, and now we must compute the total time derivative of the Lagrangian. And that's going to be q of t, q dot of t, and here's the time itself. Okay, so you see what's going to happen. There will come a point where we get this partial L, and here's the minus sign. We really need that minus sign to work out here for us. There's the minus sign, and we will get the partial derivative of the Lagrangian. Okay, so let's see what we got here. There's going to be a term. I'll just put ditto, ditto. We're copying those over. And now we're going to get three terms, right? There will be a term here. So there's a minus sign. Let's organize the calculation like this. We do have the minus sign. And now there are going to be three terms when we differentiate this. First occurrence of a time right here. So there's a partial L, partial Q. Q is the name of the first input. And the derivative, there's a Q dot. Then there's another term, partial L, partial, the second input is called q dot, and the derivative, q double dot. And finally, there's one more term. We got a partial L, partial t. Okay, and so here's where we get the nice cancellations, right? Here's the partial L, partial, the q double dot cancels off this one very nicely, and this one cancels off this one very nicely. Again, we're using the Euler-Lagrange equations, right? The total time, this is precisely, this cancellation here is using the Euler-Lagrange equation, and all that remains is that term there. Okay, so it's a cool calculation showing that this total time derivative of the Hamiltonian is minus the partial of the Lagrangian. Who would have thought? Okay, so for us that's important, right? Because what we're talking about for our 1 degree of freedom problem, we want to really understand this statement, right? That we have a 1 degree of freedom problem. I'm moving this so we get to the right. Here's where we were. We have a 1 degree of freedom problem. The total energy is conserved. And that's why people draw these diagrams. When you draw a horizontal line across this picture, this is useful because we have quite generally that the total mechanical energy E is equal to T plus U, okay? And so at the classical turning points, the kinetic energy is 0, okay? Kinetic energy is 0 at the classical turning points, and then the gap between this line, right? This gap tells you how much, so if this is your energy drawn with the horizontal line, then that gap tells you how much energy is available for the kinetic. Again, it's the gap between the energy and the U, okay? So this kind of a diagram is based upon the idea that the total mechanical energy is conserved, and it helps you to visualize the motion. So for negative energies, we have this oscillation between two classical turning points. And for positive energies, we have this unbounded motion. All right, so that brings us to the end of the hour. I'm going to pause the recording. I click here. Actually, I'm going to stop the recording.